Hello, and welcome to the presentation of Aurora, a toolsuite for automatic code generation and validation of model-based critical interoperable components. The project has received funding from the European Union's Horizon 2020 Research and Innovation Program. My name is Michał Kurowski, and I will present the main contributions of N7 Space to the activity. The agenda is as follows. First, I will introduce the project objectives. Then, I will describe briefly the taste toolchain. Next, I will demonstrate some of the new features implemented within the scope of the project. Support for multicast communication, archetypes, partial vector update, and as functions, as well as taste Leon 3 runtime, function tester, and Simulink importer. Finally, I will present the reference component set. The Aurora project aims to provide a European toolsuite for the process of development and validation of a critical autocoded flight software product in the space domain and the demonstration of autocoding technology in an industrially relevant environment. In short, how to develop better flight software faster by leveraging autocoding technology. Highlights of this presentation include Simulink to C-code transformation via Adacore's QGen software and enhancements of ESA's taste and BSC toolchain. Taste is a toolchain developed under the guidance of European Space Agency, with lineage tracing back to the EU FP6 ASART project. It contains contributions from multiple entities located in several European countries. It has been selected as the base to be extended with the capabilities identified as crucial for developing standardized, component-based onboard software. The toolchain includes Space Creator Integrated Development Environment, ASN1 SCC, ASN1 and ACN compiler, Kazoo template processor, data modeling tools, and other utility software. Contributions of Aurora to the taste toolchain include extension of the taste component model, such as the support for multicast communication, archetypes, and layers, improvement of QGen integration with taste by adding the support for S functions, partial vector update, as well as Simulink model import and numerous bug fixes, the addition of function tester, and the implementation of a brand new runtime for GR712 RC Leon 3 class processor. Multicast support. Multicast extends the original point-to-point taste communication to support one-to-N and N-to-M communication patterns useful in modern architectures. Let's create a new project. Let's remove the comment block to clean up the workspace. Now let's add a few components for sending and receiving data. Components in taste are called functions. Let's add a few interfaces. The trigger cyclic interfaces are meant to make the sender components active, so that they can actually initiate actions. There are other means to achieve that. This is the simplest one, used for the sake of the demonstration. Let's set the second trigger's period to 2.5 seconds. Now let's add the multicaster interface, which demonstrates the end-to-end communication pattern. It will have a single parameter of the predefined myInteger type. Let's connect all the senders with all the receivers. Now the senders can send the same data to both receivers at the same time or select just a particular receiver. Receivers, on the other hand, can query which component sent them the data. Let's also change the default recipient queue sizes to 10 so that they won't be dropping messages when multiple are sent at once. By default, the implementation of a new component is set to SDL, specification and description language, which allows to define the component's behavior via extended state machines. Let's edit the implementation of the first sender. The process skeleton is built automatically. The starting state is wait. Let's add a reaction to the trigger signal. We can send the multicaster signal to all connected recipients. Let the transmitted value of 0 mark our message as intended to all recipients. We can also send the multicaster signal to just one selected recipient. Let the transmitted value of 1 mark our message as intended to receiver 1. Let's complete the transition and check the state machine for correctness. Now let's edit the implementation of the second sender. Let's add a reaction to the trigger signal. Let's send 0 again to all the recipients and 2 just to the receiver 2. Let's complete the transition and check the state machine for correctness. Now let's look at the receiver side of the communication. First, let's define the variable of type myInteger. We can use it to capture the value carried by the multicaster interface. Now let's add a decision based on the message sender. The sender variable is built in, and the underlying type is automatically generated based on the interface view. For sender 1, let's write R1 indicating receiver 1, S1 indicating sender 1, and finally the value. Let's repeat that for other sender values, which in our case will indicate sender 2. Let's complete the dummy transition and check the state machine for correctness. We can now repeat the process for the second receiver. Now that all components have their implementations, let's build the project. The build was successful. Let's close the space creator and execute the binary directly from the terminal, so that it will be easier to inspect the output. The default name is demo. It can be changed in the deployment view. We can see sender 1 working once each second, and sender 2 working once 2.5 seconds. Receiver 2 received 0 from both sender 1 and 2 as expected. It also received 2 just from the sender 2. Receiver 1 received 0 from both sender 1 and 2, and received 1 from sender 1, again just as expected. Archetype support. Archetypes define sets of interfaces that can be enforced for components. They can be thought of as Java interfaces or C++ abstract classes. Let's create a new project and remove the command block. Let's add an event archetype library to the project. The library is bound to the interface view. A couple of example archetype libraries were developed within the scope of the Aurora project. Now let's create an architecture with a bus, an event source, and 2 subscribers. Let's assign the relevant archetypes to the components. Interfaces of the archetype are automatically added to the hosting component along with the type skeletons. A bus provides interfaces for event subscription and reception. It also requires an interface for event dispatching. An event source requires an interface for event notification. An event receiver provides an interface for event reception and requires an interface for event subscription. Now let's connect the interfaces. Please note that event subscription requires an N-to-1 communication pattern and event dispatching a 1-to-N pattern. Let's inspect the interface parameters. Transmitted events are defined via T-event message type. Event subscription requires an ID and a subscription flag. Partial vector update support. Partial vector update allows for more flexible, efficient, and modular interfacing with Simulink models by allowing to update or query just the relevant parts of the model's input-output vectors. This is particularly useful for complex control models with vectors spanning hundreds of items. Let's create a new project and remove the command block. Now let's create a manager, some sensors, and some actuators. Finally, let's add an AOCS component. Let's connect the components. Let's change the AOCS component implementation to QGen C, meaning a Simulink model and C code generation via QGen. Let's add the main full interface for calculating the control signals. Let's add 3 inputs, X, Y, and Z, and 2 outputs, A and B. This interface will define the ports of the Simulink model. Now we can add partial interfaces, referencing the full one. Sensor 1 will update the values of X and Y. Sensor 2 will update the value of Z. Actuator 1 will query the value of A. And Actuator 2 will query the value of B. Model processing step will be invoked by the additional step interface. Each component can update or query only the relevant data, avoiding intermediaries and increasing system modularity. The manager may cyclically perform the following sequence of actions: trigger sensors to update the relevant parts of the input vector, trigger the calculation step, and trigger the actuators to query the relevant parts of the output vector. S-function support. S-functions provide the ability to call C code from within Simulink models. This functionality was used in the Aurora project to add the support for required interfaces to QGen C-based components, allowing for greater flexibility in the architecture and data flow design. Let's create a new project. We have a predefined custom integer type named myInteger, which we'll use as the main data type later on in our project. Let's clean up the workspace by removing the comment block and then create the system architecture. The controller component will have a C-based implementation and a cyclic protected interface. QGen C component will have a QGen C-based implementation, meaning a Simulink model translated to C using QGen C software. Let's add a simple provided interface to the QGen C component. It will have a single input and a single output of type myInteger. Now let's add some utility components to be implemented in C. They will provide protected interfaces that will connect to the corresponding required interfaces of the QGen C component. Now that our logical architecture is complete, let's generate skeletons for all components. Skeletons for the QGen C component are created by first generating a MATLAB script and then executing it using MATLAB. This process may take a few seconds. Let's add some implementations. The controller, once triggered, will call the interface provided by the QGen component, passing 10 as the input and printing it along with the retrieved output. The interface provided by the first utility component will simply output the input multiplied times 2. Similarly, the interface provided by the second utility component will output the input multiplied times 3. Now let's edit the Simulink model. The input parameter is available as an input port, and the output parameter is available as an output port. The two required interfaces of the QGen component are available as S-functions. Let's connect the S-functions inputs to the model input port. The S-functions outputs must be combined before connecting to the single model output port. Let's use addition for that. Let's save the modified model. Now, let's build the system. Build is successful. Let's execute the binary. For the input value of 10, the output is 50, which is the sum of 10 multiplied by 2 within the first utility component and 10 multiplied by 3 within the second utility component. Taste Leon 3 runtime. Taste Leon 3 runtime allows to easily target GR712RC Leon 3 processor. It is based on a qualifiable version of Archetypes distributed within SRAM's simultaneous multiprocessing qualification data package. The developed software can be executed using sys emulator, which was extended within the scope of the Aurora activity. Let's create a new project and remove the comment block. Let's create two components, controller and actuator. Let's add some interfaces. Controller will be the action initiator. Let's change the component implementation to C. At the time of making this presentation, the Leon 3 runtime did not support SDL, as the qualified version of Archetypes did not support ADA, to which SDL is transpiled to. Now let's add some code. The controller, once triggered by the cyclic interface, will call its process interface connected to the actuator. The actuator will handle the process interface by printing a simple message via the built-in Artem's BSP I/O. Now let's add a deployment view. A deployment view describes the physical architecture of the system. Let's add a single GR712RC processor node and bind the actuator and the controller components. Let's change the output binary name to ASW. Let's build the project. The binary is built. Now we can execute the binary using sys. The simulator's UART is connected to standard output. The simulated CPU is set to Leon 3. Now we can see the output. The simulation is not real-time. Function tester. The function tester plugin can be used to validate the components implementing algorithms for control laws or utility math routines. Let's create a new project and remove the command block. Now we'll define a new floating point type in ASN1. Let's save the file so that the type is available in the interface view. Let's create two components, Manager and AOCS. Now let's connect them via a protected interface implementing a trivial control law. There are two inputs and one output. Let's provide implementation of the AOCS component using C. The output will be the difference between the target and the reading multiplied times 2. Now let's add a test dataset. The data needs to be provided using a CSV file, a common text-based tabular format. Each column corresponds to an interface parameter. Values for the output parameters are considered to be the expected ones. Each row is a single test vector. Now we can select the interface and test it against the created dataset. Tests can be run on various targets, including embedded ones. The data is retrieved via debugger. Once the data and target are selected, a utility test system is created, compiled, and executed. The process takes a few seconds. Test results are presented in the form of a simple HTML page. Here we can see the mismatch between the expected and actual values for the second data row. Simulink Importer. The Simulink Importer plugin aims to facilitate integration of existing Simulink models within taste-based systems. Let's start by creating a simple Simulink model. Let's create 3 input ports connected to the corresponding output ports via gain blocks, multiplying their values times 2. The first input will be a floating point scalar. The second input will also be a floating point scalar with an explicitly set dimension. The third input will be a floating point vector. Let's change the default names. And finally, let's save the model. Now that we have the input Simulink model, let's create a new taste project. Let's import the model. First, we select the file. Then, we choose the name of the component which will host the model. The import functionality relies on a MATLAB script for extracting the interface properties and data types. The import is successful. We have a component with a protected provided interface matching the input and output ports of the model. The scalar parameters are of a built-in MATLAB double type. The vector parameters use custom types, generating using the information extracted from ports definitions. The component implementation is automatically set to QGen C. ASN1 and ACN files with both the built-in and the generated custom MATLAB types are automatically added to the project. The Simulink model itself is copied to the test project directory. Now we can use the component in our system architecture. In addition to the presented functionalities, a reference component set was implemented within the scope of the project. It contains a data store component, supporting events and a CRUD pattern: create, read, update, and delete data item. The data store component relies on time service, which provides CUC and CFS timestamps. Both components are meant as a reference to demonstrate potential implementation patterns. A real-world data store and time service would either have to be heavily tailored or much more complex to accommodate various mission needs. This concludes the presentation. Thank you for your attention.